So could you please give a very up Tuesday afternoon second lecture hello to Professor Katie Mack.
Oh,
great.
Hello. How is the sound now? Is it all right in the back? Good. Okay. Hopefully it'll stay that way. We'll see. If the robots come out again, we have other options. So I'm going to talk to you a little bit about the end of the universe and some ways that that might happen. Just to be clear, I'm not talking about the end of the world. We actually know quite a lot about how the world is going to end. I mean, there are several possibilities for, massive disasters, but at the very least, we know that within about 1 billion years, the sun will get bright enough and large enough to boil off the oceans of the Earth and leave the Earth lifeless, magma-covered rock. Okay, so we got about 1 billion years for the Earth. But you could always think maybe somehow we get out into the cosmos, we go somewhere else, we find a way. And so the question then is, how long do we have after that? What happens to all of this? So I'm trying to see if we can get the lights any lower, because I think we did have it lower before. Oh, there we go. It's working? Okay, excellent. So I'm going to talk about 4 different possibilities for the end of the universe. They are the Big Crunch, the heat death, the Big Rip, and my personal favorite, vacuum decay. So we talked before about where we are in the cosmos. I showed you this lovely image of the Milky Way and the Andromeda galaxy, which is our nearest neighbor large galaxy. And we live in a galaxy that looks very much like this. Now, when we look out into the cosmos, we see galaxies everywhere, right? This is an image from the Hubble Space Telescope, the Hubble Ultra Deep Field. And this image is interesting because it contains something like 10,000 galaxies. And you might not be able to see all of them by eye, but if you zoom in, as I mentioned before, like every one of these little specks is a galaxy, its own collection of millions or billions of stars. And there are a couple of things that we learn by looking at these deep images of the distant universe. One of the things that we see when we look at these very distant images is that we can actually see the past of the universe by looking at pictures like this. The reason for that, of course, is that light takes time to travel. So every time you look at something far away, you're looking at something far in the past because it took light some time to get to you from there. And this is usually talked about in the context of astronomy, looking at stars or galaxies, but it's true all the time, right? It turns out that light travels about 1 foot per nanosecond. So if I'm looking at the front row, I'm looking at about maybe 20 nanoseconds ago. If I'm looking at the back row, I'm looking at maybe 100, 150 nanoseconds in the past. So everything you look at is in the past. It is impossible to look at anything in the present. Light just doesn't work that way. But when we look at these very distant galaxies, we could be looking at billions of years ago. So that's one thing that we learn when we look at these very deep images. We learn about the past of the universe and what it was like in the past. The other thing we learn is that distant galaxies are all moving away from us. So the universe is expanding. Okay, so I have a very sophisticated animation for that. Okay. The galaxies are getting farther apart from each other. They're getting farther apart from us. The way we see that is through the redshifting of the light. So this is a Doppler effect of light, where if something is moving away from you, the wavelength of the light gets stretched out to longer and longer wavelengths. It's called a redshifting because in visible light, red is on the longer wavelength part of the spectrum. And so that means that we need telescopes that can see like infrared light to see very, very early galaxies. And the light from the past tends to be redder and redder and stretched out some more. So we know that galaxies are moving away from us, galaxies are moving away from each other, and we know that the universe is expanding, and there's more and more empty space all the time. It's getting sort of less dense with stuff as time goes on, right? So that means that in the past, it was more dense with stuff. Things were closer together. The space between galaxies was less in the past. The amount of space that all the stuff was compressed into was smaller in the past. And so this is actually the whole root of the idea of the Big Bang theory. So the Big Bang theory is usually brought up as a story about a sort of singularity and everything comes out of that. That's a very specific piece of a more complex theory that there's complicated things when you talk about that part. But the Big Bang theory, if you're a cosmologist, is a very simple idea. It's the idea that the universe was smaller and denser and hotter in the past. Okay, if you just take the expansion as you see it, you dial it back, and everything was closer together in the past. And you get to this idea that in the past the universe must have been very hot, filled with plasma, very dense, right? So ever seen the TV show The Big Bang Theory? So the beginning of that theme song is actually very correct. It says the whole universe was in a hot, dense state. Then nearly 14 billion years ago, expansion started. Then it goes on and talks about other things that we don't care about. But the idea is that the universe was hot and dense in the past. And so you take those things together, the fact that the universe is expanding, it was hot and dense in the past, and the fact that when we look far away, we look into the past, you can ask yourself, can we see when the universe was hot and dense in the past? Can we look far enough away that we can see that? And we can. So this is a diagram from the Hubble Space Telescope people, just kind of giving a schematic idea of what it means to look into the past. So we have the modern universe here. Here's the Hubble Space Telescope. This purple band, that's the Hubble Ultra Deep Field that I showed you a little earlier. And the Hubble Ultra Deep Field is showing us galaxies that existed in about the first 500 million years of the universe. Right? But you can look farther away, and you can see the parts of the universe where galaxies hadn't formed yet. And you can look even farther away. You can look into this radiation era, the time when the universe was full of light and heat and radiation. And we can actually see that, which is astounding to me. So it's a little bit, this diagram might be a little bit confusing if you have the picture in your mind of the Big Bang being a point. Do not think of the Big Bang as a point. There's lots of reasons not to think of the Big Bang as a point. The Big Bang was an event. Okay? It was a time when the whole universe was hot and dense, which means that in any direction you look, you can look far enough away that you see a point when the universe, where, to your perspective, because of the time it took the light to travel to you from there, the universe was hot and dense, and you see the universe being hot and dense there. What it means, if you take this diagram and you sort of extrapolate, you should see that hot, dense light in any direction. In any direction you look, you should see the universe glowing with light. Now, the light's not going to be visible light because the universe has been stretching, that light has been redshifted. What you expect to see is that that light should be in the microwave or radio part of the spectrum because of how much the universe has stretched out. And we actually do see that. So in the 1960s, a couple of astronomers saw that there was this background light in every direction that was this sort of universal glow coming from all parts of the sky. And it was about the same in every direction. I'm going to show you a sort of a picture of what that light looks like in every direction. I'm going to color the microwave part of the spectrum as purple just so you can see it. Kind of looked like this. This is an all-sky map. It looked about the same in every direction. We'll get into there were some tiny variations, but basically they saw that there was this light that was coming from every part of the sky, microwave light, and it was about the same in every direction. They were looking for other things. They were just using this microwave telescope, and they saw this light. And you can ask, how do we know that it actually is this light from the early universe? How could it could be something else, right? It could be a bunch of stars. It could be some kind of like haze around our galaxy. Well, what we've done over the years is we've taken that light and we've taken the spectrum of that light. Okay? And the spectrum of the light looks like this. So this is the spectrum. This is the intensity of the light as a function of frequency. The little dots here, the little sort of, I guess they're diamond shapes, those are the data points. And the bars are error bars, just the uncertainty in the measurement. But those error bars are expanded by 400 times, just so you can see them, because they're actually very, very small. And what this spectrum is showing us is just showing us, how much of the light is coming at different parts of the sort of microwave part of the spectrum. So, sort of higher frequency light over here, lower frequency light over here. And the line that travels through these points, that black line, is a blackbody radiation curve. So blackbody radiation is the kind of radiation you get when, for example, you take a poker and you stick it in a fire, and that poker glows with heat. It's thermal radiation. It's radiation that comes from just thermal motions of atoms within a material. And so everything that's just glowing because it's hot produces blackbody radiation. And this microwave background spectrum is the most perfect blackbody radiation spectrum ever measured in nature. So what that's telling us is that we're looking at light that is coming from a universe that was glowing with heat. Every part of the universe was just glowing with heat. It was some kind of hot material in every direction, and that light has been stretched out to the microwave part of the spectrum. So it's a very compelling piece of evidence that the universe really was hot in the beginning. And we can see it. And, oh no, something has gone wrong with the clicker, sorry. Hold on a sec. Okay. So we can take that light and we can, that image, and we can stretch the contrast by a lot. So if you stretch it out by about part in 100,000, you get these variations. So this is showing the contrast to, again, about a part in 100,000. You can start to see that there are parts of this picture that are sort of hotter, parts that are cooler. Over the years, we've had more telescopes show us different, higher resolution images of this cosmic microwave background, and this is the most recent one from the Planck telescope. And what it's showing us is that early universe, that hot, dense soup of material in the very beginning, was not totally uniform. There were places where there was a little bit more density and a little bit less density, places where matter was clumping a little bit. And we can see all these little dots, and these dots are actually the signatures of sound moving through the matter, like these sound waves. It's called acoustic oscillations. The universe was so dense that it was loud. There was this sound kind of bouncing around. And by looking at the patterns in these sound waves, we learn about what the universe was made of, because the sound moves through materials differently when they're made of different things. So we learned something about how much of the universe was made of hot plasma and how much was dark matter and so on. And we can use that to learn about the past of the universe, but also the overall structure of the universe, and try and learn something about how the universe might evolve into the future. So again, this brings us to our first end of the universe scenario, which is the Big Crunch. So the idea behind the Big Crunch is fairly simple. The universe is expanding now. Things are moving away from each other because the universe is expanding. But, all of these galaxies have gravity, and they are pulling on each other with gravity. And so, they're working to slow down the expansion, right? And so you can imagine that maybe the universe expands for a while, but it gets to some point where that gravity just becomes too much and it starts reversing the expansion. And if that happens, then instead of the galaxies moving away from each other and being redshifted, they would start to be blue shifted, they would start to come toward us. And after a while, things would start to get very crowded. And a number of things happen if this occurs. The first thing that you might notice is, as you look at this very sophisticated diagram, Some of those galaxies are getting real close together. If the universe starts to collapse, the first thing that will happen is that a bunch of galaxies will start to merge with each other, and we'll get these galactic collisions. This is an image of a galactic collision that is already in the sky. There are collisions of galaxies that we see all the time, and it's not because the universe is collapsing, but it's because galaxies tend to be formed near each other, and so they're already kind of gravitationally bound. And sometimes they are gravitationally bound enough that they fall into each other in sort of a short amount of time, cosmically speaking. This is a pair of galaxies called the mice, because they have long tails. And you can see these long tails are these long streamers of stars. They're called tidal tails. And as the tidal forces of the collision sort of distort the galaxies, you end up with these long tidal tails coming out. We have entire galaxies, entire catalogs of these galactic mergers. We call them train wrecks. So you can see in some of these pictures, you get some of these long tidal tails coming out. You also get some interesting things that happen when the gas in these galaxies collides with each other. So galaxies contain a lot of gas, generally speaking. And when two galaxies hit each other, that gas can create a burst of star formation. And so in some of these pictures, you see like a lot of blue light, and that's these hot young stars that form in these bursts of star formation. And then you also sometimes see these lanes of dust, and that's because some of those stars that form very quickly also die very quickly and create supernovae, and then a lot of dust in those galaxies. And so a lot of things happen when galaxies collide. We're probably going to get a close-up view of that in a few billion years, because the Andromeda Galaxy that I showed you before is coming for us. So the Andromeda Galaxy is currently moving toward us at about 110 kilometers a second. And astronomers predict that probably in the next 4 billion years or so, Andromeda is going to collide with the Milky Way. And I said probably, it's actually, the probability of this has gone down a little bit based on recent results, recent simulations. They're saying maybe it's like a 50-50 chance that it'll hit in 4 billion years. It might actually just kind of miss and then come back around. But in any case, we are moving together with gravity. There was a nice simulation done a few years ago by some researchers where they simulated what it would look like if you could see that happening. So, right now, the Andromeda Galaxy is just a little smudge in the northern sky. But if you were able to watch over time, you would see it come closer. Now, this is 2 billion years, so this is like, the Earth is dead, but like maybe you leave a sort of, a webcam in orbit to watch this or something. Like, this is not something that we would see, but, at some point, so Andromeda gets a little closer, and then, oh no. And here you can see that those bursts of star formation, you can see the dust lanes, things are getting exciting, lots of stuff is moving around, and then it kind of bends back out, it comes in, hits once, and then comes out again, and you can start to see those tidal tails and the distortion of the Milky Way galaxy. Then by 5 billion years or so, things are starting to settle down. The stars have been burned through mostly already, and after a while, you end up with a sort of quiescent elliptical galaxy where the stars are mostly dead, and you just have a big clump of dying stars. So that's likely in our future, but it's not something that we would necessarily have to worry about, even if we were still here. Maybe we'd move to some other planet in the galaxy. But the collision of galaxies it's a big light show, but it's not necessarily something that would kill stars, for example. When it turns out when galaxies collide, it's very unlikely that individual stars hit each other. There's just a lot of empty space, even within a galaxy. So, you could end up, too close to a supernova, or there could be some kind of jet from the supermassive black holes, but most of the time, it is possible to survive a collision of galaxies. So in a big crunch scenario, the galaxy collisions are not what's, the real existential threat. The big problem in a collision of galaxies is the radiation, or in the Big Crunch scenario is the radiation. So when the universe gets more compact, all that light that's been diffused through the universe, the cosmomicrowave background that's currently just a few photons in the microwave part of the spectrum, all that light gets compressed again and gets brought back, and made more intense. It also gets shifted to higher frequencies because it's been stretched out by the expansion of space, and it gets compressed again if space is collapsing. But there's also all the light that from all of these stars that have been shining, right? I mean, stars produce visible light; they produce ultraviolet light. There are X-ray. There's X-ray light coming from stars. There are other processes in the universe that create gamma rays. You have a lot of hard radiation that's been produced since the beginning of the universe, and all that gets compressed as well. And so there's some point in the collapse of the universe in a Big Crunch scenario where the light from all of the starlight, that's just ambient light in the universe, gets so intense that it actually is enough to ignite the surfaces of stars in thermonuclear explosions. And that's really not survivable at that point. And that is a real calculation. An astronomer did that calculation in 1969, back when we thought that the Big Crunch was the most likely scenario. He decided to just work out what it would be like. And it was real bad. On the bright side, we think that's probably not going to happen. Our current sort of default scenario, default assumption about the end of the universe is something called the heat death. And the heat death is also a fairly simple idea. It's the idea that the expansion does not turn around. So, the universe is expanding, and the idea behind heat death is that it keeps going. And we have good reason to believe that it probably will. And the reason for that is that we've been trying to figure out how the expansion is changing over time, how quickly the universe is expanding, and how the balance comes out between the expansion of the universe and the gravity of everything in it. In the 1990s, astronomers were specifically trying to figure out, is the universe going to expand forever, or is it going to turn around and collapse and make a big crunch? And what they were doing is they were trying to measure what's called the deceleration parameter. So they're looking at the expansion rate of the universe, trying to figure out how quickly it's slowing down. And they had good reason to believe it should be slowing down because all of that gravity is sort of putting on the brakes. And that seemed to be the only reasonable hypothesis. But they did the measurement, and they found out that actually the expansion was speeding up. It was not slowing down at all. The expansion was getting faster and faster over time. And I just want to say that's extremely weird, okay? Because in the universe, there's only sort of one really long-distance force that we know about, and that's gravity. Right? I mean, light is a long-distance force, but it doesn't do anything on these scales. It doesn't do anything interesting. But gravity just always pulls. Gravity doesn't do anything but pull, as far as we know, in sort of standard scenarios of gravity. And we don't know of anything that does stuff that other than pull with gravity. Matter pulls with gravity, energy pulls with gravity in some way. Everything that we've ever sort of dealt with pulls with gravity. It sort of compresses space. It makes dents in space. So it's weird that the expansion of the universe should be speeding up. It's kind of like if you take a ball and you throw it in the air, it's moving upward, it's being pulled and slowed by gravity, it should stop and come down. Or even if you're really, really strong and you can throw it at 11.2 kilometers a second, the escape velocity of the Earth, it should always be slowing down a little bit, right? It shouldn't speed up. If you take a ball and you throw it up into the air and it shoots off into space, then something else is happening. Something other than just gravity and motion is happening. And so it turns out that something else is happening in the universe. Something is making the expansion of the universe speed up. We don't know what it is. We call it dark energy. Our best guess at the moment is that dark energy is what's called the cosmological constant. When Einstein wrote down his equations of gravity, he put in a term called the cosmological constant, which would just sort of balance gravity, and I'll get into this a little bit later, but it would be a sort of an opposite thing to gravity, and maybe that's what this is. Maybe there's just something in the universe that creates sort of a pushing instead of a pulling. A cosmological constant is something where there's a certain amount of sort of pushing in the universe at every point. Space-time itself has a little bit of stretchiness built in, and as the universe gets bigger, there's more stretchiness because there's more space, and it pushes, and the universe just accelerates in its expansion. So whatever dark energy is, it is emptying out the universe. It is creating more and more space, moving things apart from each other. And if dark energy really is a cosmological constant, then we know what's going to happen. The universe is going to get bigger and bigger. It's going to get colder and colder as the radiation diffuses through it. It's going to get emptier as galaxies get farther apart from each other. And in about 100 billion years, the universe will get so big and things will be moving away from us so quickly that we won't be able to see other galaxies anymore. In about 100 billion years, if you took the Hubble Space Telescope and put it in the sky and looked out into the distance, you would see nothing at all. You might see a few dying stars at the edges of our galaxy, but you would not see any other galaxies at all in 100 billion years. In 100 billion years, you also won't see the cosmic microwave background. There will be no way to prove that the universe has been evolving. There will be no way to prove that other galaxies exist. The expansion will sped up so much that everything will be moving away from us so quickly that we won't be able to see anything outside the Milky Way, or the Milky Way Andromeda clump, whatever's left. And then eventually the stars in our own galaxy will die. The black holes that form as a result of the collapse of stars and the black hole in the center of our galaxy will evaporate, most likely based on our understanding of how black holes evolve. And the universe will be left a cold, dark, empty, lonely place. That's the heat death of the universe. Very sad story. You might think it's odd that it's called the heat death, but it's actually very cold. And the reason for that is that the concept of heat, in this case, is really talking about disordered energy. And the idea is that over time, because of the second law of thermodynamics, everything just sort of evolves toward more and more disorder, right? The second law of thermodynamics says that entropy always increases into the future. And heat is just disordered energy. And so over time, everything evolves into kind of the waste heat of everything. And the term heat death technically means you get to a point of maximum entropy, where everything is so disordered and just completely disintegrated that there can be no more disorder added to the system. And that's an interesting point to reach, because the second law of thermodynamics says that the arrow of time, the direction of the future, is the direction in which the entropy is increasing. So if the entropy can't increase anymore, you kind of lose the idea of the future. Time still passes, but it doesn't have a direction anymore. And essentially nothing interesting can ever happen again. Yeah, so that's the heat death. It could be worse. There are scenarios that are more violent. The big rip is an idea that comes from the possibility that dark energy is maybe not a cosmological constant. So I mentioned before that Einstein came up with a cosmological constant as like a balance of gravity. So I'm going to explain this in terms of galaxies. Actually, when Einstein was thinking about this, he didn't know that other galaxies existed. It took a while to figure that out, because things looked like just sort of nebulae in the sky. They didn't have really powerful telescopes. So he kind of did this argument with stars, but it works better with galaxies, so we'll just use that. So the idea is that there are a bunch of galaxies in the universe, and they're all pulling on each other with gravity. And when Einstein was first writing down his theory, not only did he not know that other galaxies existed, he thought the universe was static, that it was unchanging over time, that nothing was being created, nothing was being destroyed, everything was just sitting there in the sky. And that didn't make sense in a universe in which gravity is always attractive, because all those galaxies should be pulling on each other, and they should have collapsed into a clump a long time ago. You can't have a static universe with just gravity. So he invented this new term in his equations called the cosmological constant to just perfectly balance the gravity, to kind of hold those galaxies up and make sure that nothing fell together. Just imbued space itself with a little bit of stretchiness to hold everything up. When it was discovered that the universe was expanding, the expansion itself was the explanation for why everything wasn't in a clump. It's moving apart, not coming together. And so he threw out the cosmological constant, said it was a mistake. And then when the expansion of the universe was found to be accelerating, we had to put it back because we needed something to push away the other galaxies. So the thing about the cosmological constant that's constant is the density, because the idea of the cosmological constant is like each part of space has this cosmological constant built into it. So whenever there's more space, there's just more cosmological constant. So the density, the amount of sort of energy in cosmological constant over time stays constant. And that's not true of other things in the universe. So if you look at a graph of density versus time for matter, for example, matter goes down over time because the universe gets bigger, there's the same amount of stuff, there's more volume, therefore the matter goes down as the volume gets bigger. The amount of radiation, the density of radiation also goes down over time. It goes down faster because we're talking about the energy density. And so not only is there more space for that radiation to be in, but also it's being stretched out by the expansion. So it's stretched to lower energies. So the energy in radiation decreases even faster over time. But a cosmological constant just stays constant. And so that's why in the early universe, the cosmological constant was really unimportant. The radiation was very high, and so the radiation was higher than the matter, and both were much, much higher than the amount of cosmological constant. So dark energy was not important in the early universe in this scenario. But now, dark energy is most of the universe. The matter is sort of somewhere around 25%, a third, and then the cosmological constant is around 70%-ish of the universe. And in this scenario, if the universe is full of cosmological constant, then as time goes on, there's just more and more cosmological constant compared to everything else. And after a while, the cosmological constant is the only thing that's important in the universe. And that's when you get to heat death, where like just everything else is basically faded away, and the universe is just expanding and expanding and expanding. But it's possible dark energy is not a cosmological constant. And there's actually been some interesting results recently from a galaxy survey called DESI that has suggested that maybe dark energy is changing over time in some way that doesn't fit with the cosmological constant. And there are a couple of ways that can happen, but one possibility is maybe the density of the energy density of dark energy goes up over time. And if it does, that's something called phantom dark energy. And phantom dark energy has a very interesting effect on the universe. So the thing about a cosmological constant, because the density stays constant with time, you're not getting like more dark energy over time in this room, right? The universe is expanding, so like the spaces between galaxies are getting bigger, but this room is not getting bigger. The reason for that is that this room formed in an environment in which dark energy was already there, and like the Earth or the room or whatever just won that fight, right? The universe is trying to expand, so you form something that's bound, like a gravitationally bound system or a system bound by atomic bonds or something. And if you can make it form, you can't build up more dark energy inside it because the density of dark energy inside it is going to be the same, right? So in this room, we have way more matter density than dark energy density, so the dark energy doesn't do anything. In a galaxy, you can draw a sort of sphere around the galaxy and say, okay, the matter won. The dark energy isn't doing anything more because there's more matter than dark energy, so it's not going to be able to push things apart. In the big empty spaces between galaxies, there's way more dark energy that can cause expansion. But our galaxy is not being expanded by dark energy. But phantom dark energy is a different story. If the density of dark energy can increase over time, then it could build up within a galaxy. It could build up within this room. And the idea is that in phantom dark energy, in that scenario, the dark energy builds up and builds up and builds up such that you can calculate that in a finite amount of time, it builds up so much that it can tear the entire universe apart. Essentially, you get, you know, oh, no, sorry. Yeah, here. In increasingly small spaces, you get more and more dark energy happening, and it just pulls things apart. First, you pull apart clusters of galaxies, and then planets, and then atoms, and then space itself. And this is an idea that's not favored for a bunch of reasons in theoretical physics. We don't think that it makes sense to have that kind of energy in the universe. But we also didn't really think that it made sense to have dark energy in the universe before we figured out that dark energy is in the universe. So, I mean, it breaks some energy conditions that we think are important in physics. But there are also a lot of papers being written about it right now because the DESI results for changing dark energy suggest that there might have been a phase of phantom dark energy in the past. It changed. It's not like that now, apparently, but maybe it's possible. And if it were, it would have a big effect on the universe. It would cause the big rip. And this is an idea that's been taken seriously enough that NASA made an animation about it about a decade ago. And I just really like this animation. It's not the most scientifically accurate animation, but it kind of gets the point across. So it starts with sort of regular expansion, and then the phantom dark energy part takes over. So I'll just let you see how this looks. So expansion, expansion, then, oh no.
That's it again. So this is exactly like that, but you get the idea. It's real bad things happen. On the bad side, you can calculate that based on how the news is trending right now, you can calculate what's the soonest the big rip could happen. If it turns out that the dark energy really is phantom dark energy, right? And when you calculate that, you get a number like 200 billion years. And I already told you that after 100 billion years, the universe is really uninteresting anyway. So maybe it's not that big a deal. 200 billion years, we don't need to worry about that. But there is a possibility that could technically happen at any moment. So vacuum decay is an idea that first came up in sort of the 1960s, 1970s, but got really much more interesting in 2012 when the Large Hadron Collider found the Higgs boson. This is an image of the CMS detector, the Large Hadron Collider. Just for scale, those are people. There are 3 people down there. So it's a really large machine. And the Large Hadron Collider is colliding protons together and looking at what comes out of those collisions. This is an event display from one of those collisions. Basically, they collide protons together, they look at all the debris that comes out, and they learn something about how matter interacts with itself. And this is one of the events that could be, producing a Higgs boson. You don't really see the Higgs boson, you see decay products of the Higgs boson. And when the Higgs boson was discovered, we learned something about sort of the state of the universe. I already walked you through the Standard Model earlier today, so I'm just going to show that again, just to refresh your memory. But basically, by looking at the Standard Model particle physics, by looking at how the particles relate to each other, we can learn something about the fundamental rules that govern physics in our universe. Specifically, one of the things we can learn about is the Higgs field. So the Higgs field is an energy field that's through all of space. And the Higgs field has something to do with how particles got mass in the early universe. I mentioned that. But the specifics of that are complicated. So the basic idea is that there was a time very, very early on when the Higgs field had kind of a different value. So the Higgs field is a scalar field, meaning that it has a value everywhere in space.
you might be used to vector fields. So a vector field is something like the electromagnetic field. So there's an electromagnetic field in this room, and at every point in this room, there's a value, a strength, a magnitude of that electromagnetic field, but there's also a direction of the electromagnetic field. That's a vector field. A scalar field is more like the temperature in this room. At every point in this room, there's a number that tells you the temperature of this room. It's going to be hotter close to people and colder far from people. So the Higgs field is a scalar field. It's a field that has a value everywhere in space. We think there's the same value everywhere in space. And the value of the Higgs field determines something about how other particles interact with it, which determines something about how, like, which particles exist and how they're arranged and what their masses are. So there was a time in the very early universe when the Higgs field had a different value and particles were interacting with it differently. And when that was the case, none of the particles had mass. Some of the gauge bosons were different particles. You had a situation where you couldn't possibly have atoms or molecules because essentially the constants of nature were different. And then the Higgs field changed, and when it changed, it created the conditions for particles to have mass, for chemistry and everything to work, and it set up the standard model of particle physics as we know it today. So that kind of brings up the question, could it change again? We don't want it to, because we like having particles and with mass, we like having atoms and molecules. We don't want them to not work. But there's a possibility that the Higgs field is not fully stable. And in 2012, physicists started to really take seriously this possibility. So they did things like, they made plots like this. This is from a paper in 2012, where they worked out, based on the mass of the top quark and the mass of the Higgs boson, which parts of this parameter space result in a stable universe in the green, or like an unstable universe where we should have all collapsed into black holes at the beginning, or places where the equations don't work so well anymore. You have to use different kinds of physics to describe it. And so, if the Higgs mass were like 50 GeV, GeV is giga electron volts. Just for reference, a proton is about 1 GeV. So if the Higgs mass were 50 and the top mass were 50, we'd be nice in this stable region, everything's great. Higgs mass is 50 and the top mass is 200, the universe already collapsed, everything's terrible, we're not here. Anyway, they did some calculations, they did some measurements, they measured what the Higgs mass was, and they find we're right there. So that's in a region called metastability, which means the universe is stable for now. So metastability is like, if you take something and you put it right at the edge of the table. That's metastable, right? That means that, like, it's fine, it's there, it's not on the floor, but it doesn't take much to tip it over, right? It's kind of just, it's not stable to perturbations, right? Any kind of bump means it lands on the floor. And that's where we think that our universe might be based on these calculations. That's what the result of this calculation shows us. Just to give you a sort of illustration of sort of how we look at that sort of mathematically. This is an image from a paper from 1980 where they're talking about this possibility of the universe, that the Higgs field is metastable. So the idea here is the y-axis is the potential of the Higgs field. The potential in this case is kind of telling you what values of the Higgs field are higher energy or lower energy. Very similar to a gravitational potential. So you can think of it very much like, these are valleys, and there's like a little ball that sits in one of these little valleys, right? And there could be higher valley and a lower valley. And if it's in the higher valley, it's in a metastable state because it would kind of rather be in the lower valley. Kind of like this thing, it's fine right here on the edge, but it'd kind of rather be on the floor, right? And so the idea is that if the Higgs field takes a value that's in this higher part of the potential, we call that a false vacuum. The idea is that wherever the Higgs field is, that's the vacuum state of the universe. We call it a vacuum state not because it's empty, but because it's like the background state in which everything else is happening. And if there's a higher one, that's the false vacuum, and then the lower one is the true vacuum. And the danger in living in a false vacuum is that, something could happen to cause us to kind of go over that hump and end up in the true vacuum. If you could disturb the Higgs field enough, then it could go into that true vacuum. And that would be bad because the true vacuum has different constants of nature. You don't have physics the way we understand it in the true vacuum. Fortunately, it doesn't seem like there's anything that can perturb the Higgs field in that way. Like, we don't know of anything powerful enough to specifically mess with the Higgs field to make it do that. Kind of like if you're just a little ant and you're trying to push over this bottle, it's not going to work. Like, you just don't have the strength. We don't know of anything in the universe that could push the Higgs field over the edge. But unfortunately, the Higgs field is a quantum field, and we live in a universe that is fundamentally quantum mechanical, and quantum mechanics makes some things that seem impossible happen really often. One of those things is quantum tunneling. So, probably heard of quantum tunneling. The idea behind quantum tunneling is that if you put a particle on one side of a wall, sometimes it'll just show up on the other side. It won't have gone around, it won't have gone through, it'll just be on the other side. It's got this sort of spread out wave function, and some part of that wave function is on the other side of the barrier already, and sometimes the particle will just show up on the other side. And technically, if you leave this here long enough, some of those particles will quantum tunnel through, and they'll just fall to the floor. Right? It has to be a really long time. But that could also happen with the Higgs field. The Higgs field is very happy in its false vacuum state. If you wait long enough, it might just quantum tunnel to the true vacuum state. And the universe is full of Higgs field. And at any point in the universe, the Higgs field could do that quantum tunneling event. And quantum tunneling events are not deterministic. We can't predict exactly when they'll happen. We can talk about rates, but we can't say exactly when or how or where a quantum tunneling event might happen. It's a stochastic, it's a random quantum event. But let's talk about what would happen if it did occur. Okay, somewhere in space, the Higgs field quantum tunnels from the false vacuum to the true vacuum, and it creates a bubble. It creates a bubble of true vacuum. So inside this bubble, you have the conditions of the true vacuum, a state where the constants in nature are different, physics works differently. The edge of this bubble wall, is this very high energy state that if you touched it, it would incinerate you. It's still a lot of energy in the bubble wall. And that bubble wall is expanding at about the speed of light. And that means that if you're standing nearby, there's no way you're going to see it coming. By the time you see the light from it, it is on top of you and you have been destroyed. So once you get incinerated by the bubble wall and you end up inside, then your atoms fall apart and you don't hold together anymore. So that's bad. It's the sort of thing that, because it could happen anywhere and you can't see it coming, technically speaking, it could happen, at Saturn right now, and we won't know about it for an hour and a half and we're all destroyed. Technically speaking. It does get worse. So I showed you that thought of the potential. The people who wrote that paper were these guys, Coleman and DeLucia. They wrote this paper in 1980. And what they were doing in that paper was they were calculating what happens inside the bubble, like what the space inside the bubble is like. And they determined, at least for the theory they were looking at, that the space inside the bubble is gravitationally unstable. And what that would mean is that first you get incinerated by the bubble wall, and then your atoms fall apart, and then you collapse into a black hole. And they did that calculation, and then they wrote a little reflection on the calculation that I thought was one of the most poetic pieces of physics writing I've ever seen. So I'm just going to share that with you. So they did this calculation that everything collapses into a black hole inside the true vacuum bubble, and they say, this is disheartening. The possibility that we are living in a false vacuum has never been a cheering one to contemplate. Vacuum decay is the ultimate ecological catastrophe. In a new vacuum, there are new constants of nature. After vacuum decay, not only is life as we know it impossible, so is chemistry as we know it. However, one could always draw stoic comfort from the possibility that perhaps in the course of time, the new vacuum would sustain, if not life as we know it, at least some structures capable of knowing joy. This possibility has now been eliminated. So, I do want to say you should not worry about vacuum decay. I have to say that because people write me emails and say they're worried about vacuum decay. You should definitely not worry about vacuum decay. There are a couple of reasons for that. One of them, there's nothing you could do about it, right? You wouldn't see it coming, you wouldn't even feel it, because if it travels at the speed of light, like your nerve impulses don't travel that fast, you wouldn't feel it, you wouldn't notice it, would basically just be, you would just not exist, it's like whatever, that's fine. It destroys everything, there's no tragic aftermath, there's no FOMO, it's just done. But also, we can calculate like a rate based on what we understand of the theory. And when we calculate that rate, we get something like 10 to the power of 100 years, maybe 10 to the power of 500 years, where the chance of it happening anywhere in the observable universe between now and then is astronomically low. It's probably similar to this tunneling through the table and ending up on the floor, maybe even more unlikely than that. So it's really very unlikely to happen anytime in the lifetime of the Earth, anytime in the lifetime of anything interesting in the universe. But there's another reason to not worry about vacuum decay, and that has to do with this diagram that I showed you before. Because if you'll remember, what I said about this diagram is that this little 5% slice contains the entire standard model of particle physics, and the prediction that we are in a false vacuum is based on the idea that the standard model of particle physics is the full story. The prediction you get for vacuum decay, for the instability of the Higgs field, relies entirely on there being no new physics at higher energy scales. And if there is new physics at higher energy scales, it changes the story in some way that we don't know yet. So that's one motivation, to try to understand the rest of this picture, try to understand dark energy so that we know if it might tear the universe apart someday or not. Try to understand dark matter so that we can extend the standard model of particle physics and better understand how stable our universe is, how it works, what the fundamental workings of the cosmos are. And in the meantime, we probably have quite a lot of time to explore the universe, to understand the universe, and to appreciate the universe while we're here. So I encourage you to do that, and I'm sure over the next 10 or 11 days, you're going to learn a lot of things and have some really amazing discoveries. And thank you for letting me be a little part of that.